Okay. Okay. Hi, everyone. Welcome to our distinguished seminar series. Today, we are so pleased to have Professor Zahra Ghodsi as our distinguished speaker. Professor Ghodsi is an assistant professor in the Department of Electrical and Computer Engineering at Purdue University, where she leads the Trustworthy Computing and Learning Systems Lab. And she received her PhD in Electrical and Computer Engineering from New York University. And her research interests include computer security, applied cryptography, and machine learning. And in particular, her work addresses several aspects of trustworthy learning systems with a focus on providing strong privacy and security guarantees in the presence of adversaries, as well as efficient hardware and system implementation for secure learning frameworks. So today, she's going to give us a talk on collaborating with confidence, securing federated learning systems. So I want to thank all of you for participating in our event today. And also I want to thank Professor Ghodsi so much for accepting our invitation. And without further ado, I will pass the ground to you. Thank you very much.
Thank you so much. It's a pleasure to be here. I'm very happy to share some of the work we've been doing and this topic area in general. So today I want to talk about learning collaboration in collaboration, but with security guarantees. Obviously, this work wouldn't be possible without the joint work of my collaborators and other students. So I would like to acknowledge them here. And this talk is kind of building around the idea of when you combine methods from cryptography with systems for machine learning, right? So I try to keep this talk with sufficient high-level concepts and background to make sure that it's accessible to wider audience. But basically, I want to focus on what are the opportunities and challenges of basically when these two worlds come together. So let's start with setting that should be familiar to a lot of us. We've worked in areas where we have a network of a large number of devices, usually edge devices, that are constantly generating large amounts of data, right? So you could have this across a lot of different industries, for example, in manufacturing, in healthcare, in transportation, and so on. There's a lot of new ideas of connecting these, making these individual devices, parties, and these networks, quote unquote, smart, have them be connected with each other, and basically we would enable new applications and possibilities by these such networks. And if we have such networks of devices, then each of them would generate their own data, right? So if you consider the applications for healthcare, you could have patients wearing wearable devices or monitors, or you could have different institutions, hospitals collecting health records and so on. The new applications that we were looking to enable would be possible if we are allowed to share this data, right? So if these parties can share the data that they're collecting, then, for example, in the machine learning applications, they can train a joint model on their data, and that model would have a much better accuracy performance with different metrics that we care about, compared to if that model was just trained on an individual data set, right? So we want to enable this sort of data sharing to make sure that we can train our machine learning applications, right, which rely on a large amount of data. But we want to be able to do this in applications where maybe the data that we're collecting can be sensitive, right? So it's pretty obvious when you're dealing with personal health data, right? But it could also be sensitive information of institutions, different corporations, and so on. And we can have potentially strong adversaries who seek to compromise the privacy of either individual people or institutions and so on, right? And we also have regulatory restrictions in data sharing. For example, the laws that have been passed for with regards to personal data or sharing of medical data, these essentially restrict our possibility of sharing this data that we collect at these, for example, edge nodes. So what we want to enable is to have this collaborative learning without sharing such sensitive data, right? So how do we enable multiple parties with their private data sets to jointly train a model on all of their data sets without compromising their own privacy? And this is the basic primitive, the basic idea of federated learning, right? So for those of you who are familiar, the idea here is that you have multiple clients with their own data sets, and what they want to do is share, basically train a global model, train a central model on all of their data. So one naive approach in this case would be to have all of them send their data sets to one central server, and then that server would train that global model, right? But this is, again, against that requirement that we had, that we're not allowed to share such data, so individual data. So the idea of federated learning was that, okay, these clients can hold on to their data sets on their local devices, right? What we're going to do with this central server is have it keep track of a global model, right? So what it would do is the server would send or share this global model with individual clients. What they would do is they would train this model with their local data sets, right? So at no point they are sharing their data sets themselves. And then they would send the individual updates, model updates to the server. So once the server receives these model updates, it can aggregate them and apply it to the global model and obtain an updated model, which can then be used in future rounds of training, right? So the promise here was that we are enabling this joint training without each individual client having to share their data. Now, as it turns out, this is not exactly as secure as we would like it to be, right? So if you consider a setting where you have a malicious server, this server is obtaining individual model updates from each of these clients. It's true that it's not accessing the potentially sensitive data sets, but it's obtaining at each round the model update that client is sending to the server. And prior work actually showed that from these model updates, you can reconstruct the individual client's data sets, right? So there are some examples of this work that I've shown here, but essentially they enable a malicious server to use those model updates to reconstruct individual clients' potentially sensitive data sets. So as you can see, the example here that is shown is able to reconstruct the input data set, right, the training data set pretty accurately. Okay, so we made an attempt of enabling this collaboration securely. So, but in the case of federated learning, it doesn't quite work because these individual updates themselves reveal information about the training data sets. So how do we make sure that we can do this federated learning without such, with protection against such attacks, right? So it turns out that we can use techniques from cryptography to enable exactly this, right? So There are solutions such as homomorphic encryption or masking, and among other things, that enable such computation, right, without revealing individual private sensitive values, which in this case are the updates themselves. So the idea here is that these individual model updates are obfuscated from the point of view of the server, but nevertheless, the server would be able to compute this aggregation and reveal the update, compute the update model without having access to such individual updates, right? So if you consider a federated learning setting, you would typically, applications, they would have hundreds of thousands or millions of clients. So revealing the aggregate of all of these updates to the server, which is, let's say, just summation of all of them, would obfuscate the individual updates, but computing that also is done in a privacy-preserving manner. So before I show you some two in particular ways of doing this, I'll just want to give a brief intro to the techniques, the cryptographic techniques that are used here. Again, I'm keeping this at a very high level. I just want to make sure that we're all on the same page as to the capabilities of these cryptographic techniques that we're using, right? So the first technique is called homomorphic encryption. And what it allows us to do is to compute over encrypted inputs, right? So to give you an example, let's say you have a homomorphic encryption scheme. And what you can do with that is to, let's say, encrypt two inputs, so x1 and x2, you encrypt them, and you obtain two ciphertexts, which we call here C1 and C2, right? So these are ciphertexts that don't reveal anything, any information about the inputs themselves. So the guarantees of this encryption scheme is that the ciphertext, which looks like a random string of binary values, wouldn't reveal anything about these inputs. But what you can do is now perform an operation over the ciphertext themselves, right? So what this operation looks like depends on the construction of the scheme. But let's say we are able to perform an operation over these two ciphertexts, obtain a resulting ciphertext, which if you then decrypt would correspond to the addition of the original values, right, of the what we call plaintext values, right? So you can see the power of this homomorphic encryption, right? You're able to perform operations in the ciphertext domain, which would correspond to doing operations in the plaintext domain that you're interested in, for example, addition or multiplication. Now, I want to just mention two different versions of these homomorphic encryption schemes. So one class of them are called partially homomorphic encryption, which means that they can only perform operations with respect to one operation, right? So they're only homomorphic with respect to addition. For example, pale layer scheme is an example of that. Now, if you want to do arbitrary computations, be able to do both addition and multiplication, those schemes are called fully homomorphic encryption. But it turns out that usually those schemes are going to be slower, right? So in the cases where we only care about performing one operation, we would like to stick with faster, more efficient schemes which are partially homomorphic, right? So this is exactly the reason that I'm mentioning this is because this is exactly the scenario where we have the aggregation step of federated learning, which is, for example, if it's Fed averaging, it's only doing the summation of all of these ciphertext, basically. Okay, before I show you the resulting framework for doing this secure aggregation, let me just mention one additional property that we can get from these cryptographic constructions, which is related to threshold crypto systems, right? So these threshold crypto systems, the capability that they add is basically only affecting who is able to decrypt the ciphertext, right? So in the previous example that I showed you, you would have one key that is used for doing the encryption. That's we call it usually the public key. So everybody can do the encryption having that public key. And then there's a secret key which is used for decryption. So only the person who holding that secret key would be able to decrypt the ciphertext. Now, in the idea in the threshold cryptosystems in general and threshold homomorphic encryption in particular is that we are going to distribute the trust by giving shares of this secret key that is used for decryption to multiple parties. So we would share this decryption key, let's say, among n parties, and each of them holding that share of that secret key would be able to partially decrypt a ciphertext, right? And this threshold property would allow you to collect, let's say, T of these partial decrypted ciphertext and reconstruct the plain text value corresponding to it, right? So you have this T threshold. If T of these parties come together, they would be able to do a decryption, but anything less than that would not allow it. So in this case, we would have the three algorithms that we have. The key generation is generating one public key for the encryption, and then you have shares of the secret key that you distribute that is used for decryption, and then you have the encryption and decryption that are using this public key and the shares of the private key to perform the encryption and decryption operation. Okay, so now using this technique, right? Let's say that at the threshold pair, as I said, which is additively homomorphic, we can now perform secure aggregation, right? So you can have now each of these individual clients encrypt their model updates with the public key of this encryption scheme. The server would homomorphically add these encrypted updates, individual updates, right? So there's a additive homomorphic property, so the server is able to compute this, but that would only give the resulting aggregate ciphertext to the server, right? The secret key for doing the decryption is also distributed among these clients. So what the server would do is to query at least T in this threshold scheme clients to obtain the partial decryptions, put them together, and then reconstruct the model update, right? And in this case, update the model, the global model, and share it again, and so on, right? So this is one way of doing this. The other ways are dependent on other schemes. I'm going to show you another way that you can do this, and there are pros and cons to each of these methods, and I'll talk about that. So in this case, you can use one-time paths to mask private values, and what that means is, for a very simplified version of this, if you have a private value X, you can sample a random value which corresponds to a mask, add that to your private value, and this mask input now would not reveal anything about the original input themselves. So we want to construct a protocol now that would allow individual clients to mask their updates in such a way that when the server performs this aggregation, these masks would cancel out and the server would be able to obtain the aggregate result, right? So this is a protocol due to Bonawitz et al. And the idea here is that you would have these clients compute a pairwise mask between themselves. So they can do this, for example, using key exchange protocols, if you're familiar with it, such as Diffie-Hellman key exchange. And each of these pairwise masks would be then added to their individual model updates. So one of them would add, let's say, the mask itself, the other one would add the negative of that mask, in such a way that when the server is doing this aggregation, then these masks would cancel out and the server would just obtain the aggregate results of all of these updates, right? So there's some more details here that you have to worry about if you have like clients dropping out during competition and so on. So there's some additional information detail inside this protocol to take care of those. But the basic idea is just using this masks, right? So again, these are just two different ways of achieving this secure aggregation as we wanted it, to make sure that this server is not able to access individual clients' updates. They come with different trade-offs, right? So in the case of homomorphic encryption, you have more computation potentially that either the server or the clients have to do, but then the communication in terms of number of rounds would be lower than in the case of doing more communication heavy, such as this sharing of random masks and so on, right? However, the main property still remains in that any secure aggregation method would obfuscate individual client updates, right? And what I want to show you is that this could potentially result in unintended consequences, right? So in each of these two methods, the server is not able to inspect individual clients' updates that are submitted. So let's see when that could result in some consequences that we don't want, right? So remember, again, in the federated learning setting, you could have hundreds of thousands or millions of clients participating, right? Now, think about what could happen if one of these clients is malicious or compromised. If the update that they submit is poisoned, what we call poisoned, if they, let's say, submit an out-of-range update, something that is completely wrong, then they could potentially derail training, right? So they can have various objectives of doing this. There are classes of untargeted attacks which just aim to reduce the global model accuracy, right? Somebody wants to compromise the business of another company that is training this model based on federated learning, right? Or they can even be more pernicious in that they are targeted, they can inject backdoors, so the accuracy of the global model is unchanged for the main task, but there are hidden backdoors that could be injected in this model, right? And the way that, one of the ways that you can prevent such attacks is to, let's say if you have Byzantine attacks that are just trying to compromise the model accuracy, you try to identify these malicious updates, right? So there are different ways that you can do this to achieve what we call a robust aggregation scheme. So you can check the norm of these updates, right? So if a malicious client is submitting an update that is out of bound, right, very large value, that's obviously wrong. You can inspect that submitted value and reject it, right? You can have more complex methods. Let's say if you're detecting outliers, right? You can do, for example, there are proposals based on clustering and other methods to identify updates that are malicious, right? Or you can use aggregation strategies that would be robust to outliers, right? So instead of computing an average, if you compute just a median, that's more robust. Or you can have more complex aggregation schemes based on mean around the median and so on, right? So these are what we call rank-based statistics, right? So there's, again, this is also a large field of research. There's a lot of ongoing work on achieving such robust aggregation schemes. And as usual with security, there's a race between the attacks and the defenses to enable robust aggregation in this case, right? But what we are going to think about is, what if, in this case, we are considering a scenario where both server and the client could be malicious, right? So previously we discussed the malicious server, which could reconstruct sensitive data, right? Now, in this case, we say, okay, if we take one of our solutions for secure aggregation, what happens if now one of these individual clients is malicious, right? So remember, in this case, each client is sending an obfuscated version of their update to the server, right? So if one of those values is malicious, the server has no way of figuring it out, right? These methods that need to inspect individual updates to identify malicious ones wouldn't work in this case, right? The malicious update could be aggregated into the global model and go unnoticed. So the question that we were asking is, how do we check the well-formedness of these client updates without compromising their privacy, right? We don't want to have to reveal the individual updates, but we want to enable both robustness and security in our federated learning aggregation. And the solution that we proposed is to use other techniques in cryptography, such as zero-knowledge proofs, to ensure both correctness and the privacy of the participating clients. So if you're not familiar with zero-knowledge proofs, they are a very powerful technique in cryptography, which they allow you to prove a property of a secret value, right? That sounds a little fantastical, but that's exactly what these protocols enable you to do, right? So the setting is that you have a prover with a secret value W, let's say, and they want to convince a verifier, prove to a verifier that a particular property on this private value holds, right? So for example, that this value is within a certain range. And the zero-knowledge proof protocols would enable the prover to convince the verifier of this property without revealing anything else about that particular private input. So now the system that we constructed is using these zero-knowledge proofs for the users to, in addition to submitting their obfuscated masked updates, also submit zero-knowledge proofs of correctness of the computations that they do for masking their updates, as well as the well-formedness of their updates. And we can, as we said, these zero-knowledge proof protocols enable the clients to do this without revealing any other information about the individual updates themselves, right? So what does it mean to check the well-formedness of an update, right? We can have different definitions for this, right? So we can have checks that are based on the norm of an update, right? So we want to make sure that the norm of an update is not beyond a acceptable range, or they could be based on ranked-based statistics, right? Computation of a median and so on, which is robust to outliers. Now, it turns out that most of these norm-based defenses can be easily attacked. You can have, you can construct an update that would pass the norm check, but would still be able to circumvent the training. But on the other hand, these rank-based statistics based on median and so on require a lot of comparison. And doing comparison in a privacy-preserving manner in cryptography is usually expensive. So the solution that we proposed is to, instead of computing the median over all of these client updates, is to do it over clusters of clients, right? So we would have the server randomly cluster the clients. Those cluster means are computed with secure aggregation. And then our check for well-formedness is based on the median of this cluster means, right? So after we identify this range that we accept for this round of updates, then we perform in another round of secure aggregation, only including the clients that were able to prove that their update is within this range that we come up with, right? So there's some more detail here. The protocol details are in the paper if you're interested to look at. There's additional checks that we have to do to make sure there's consistency between all of these rounds and what the clients submit. But essentially here, we're able to exclude the clients that are not able to prove their well-formedness of their update in our aggregation of the global model. And what we did is use a interactive proof protocol based on Wolverine. And the benefit here is that this proof protocol has a very efficient prover, which is usually not the case for these DKP protocols. Nevertheless, doing this ZKB checks is the bottleneck, the main bottleneck of this runtime, right? Of this system. So what we're asking is whether we can introduce an optimization that would not require the checking of each individual update. And it turns out that you can introduce such an optimization if you make an assumption of how many of those model individual parameters are malicious. Then as long as you can detect one with high probability, then you can detect the malicious client, right? So in the interest of time, I will leave these details, but it turns out that our system can reduce the number of ZKB checks, but still be able to detect a malicious client with high probability. And we show the performance of our system also against different poisoning attacks, and show that it can actually retain the benign training accuracy. And all of these training rounds can be performed under 1 second, right? So these are a sub-second runtime with low communication. So if you're interested, you can read more in our paper about the details. But in the time that is remaining, I want to also introduce another issue that arises where we're doing secure aggregation, right? So if you remember any of the secure aggregation methods, we would have to have clients participate with their public key, right? The reason for this is if you have a malicious server, they can simulate an arbitrary number of clients. This could violate the assumptions that we have on the honesty of the clients and so on. So all of these protocols would require a public key infrastructure, right? So again, this is a very common technique when we are dealing with cryptographic techniques. But here the idea is that we have certificate authorities where a participant can take their key pair, right, their public key, and their identification, and this authority, the certificate authority, would basically bind the private, the public key and their identity, right? So they're certifying that this public key actually belongs to this particular person, right? And this is very important in distributed trust when we're building cryptographic systems, right? But the issue here now is that when you're working with federated learning systems, that the identity of individual clients is tied to their participation, right? So if you have a setting where the mere participation of clients in a training round can reveal something about them, this can be a problem, right? So imagine a study of doing a learning algorithm for a particular disease, and just participating in that training, in that federated learning task would reveal something private about you. So in this next work, we were aiming to construct systems where you can disjoin these two things, right? So you can perform secure aggregation without revealing anything about individual clients' identities. And we did this through several techniques in cryptography, including zero-knowledge proofs and other things. I'll just give a very quick overview of this. And again, if you're interested, you can look at the paper, which is to appear in PITS next year. So in this case, we have multiple parties here. So we have the clients, and we have introduced the certifiers, which are certifying the datasets for each of these clients. So if you imagine a medical application, you can have hospital certify the client's datasets. And then we also separated the role of a model owner and the aggregators, right? So this is to distribute the trust. So the aggregators would take care of aggregating the model, and then the result would be sent to the model owner. So I'll just very quickly show you the operation of this. For the interest of time, I'll skip the details, and you can check them out in the paper, right? So this system we call NFL is performs in two steps. So in the registration step, we use a public bulletin board. This is again common in let's say cryptocurrency applications. So this certifiers would send their public key. The clients would submit commitments about their data sets together with proofs that they're actually the legitimate owners of this data set and so on. The aggregators would publish their homomorphic encryption key. And the benefit of our setup is that this is each client can join without having to synchronize with any other client, right? So our system does not require specific protocols for joining or leaving participants. They can join and leave at any time. And then a training round would involve the model owner publishing their the model. The clients would take this, train it locally, and then publish the encrypted model updates together with proofs attesting that they're the actual valid owners of the dataset and so on. The aggregators would take these model updates, add differential privacy noise, partially decrypt this and send them to the model owner, who is then able to obtain the updated model and publish it again. So this is one round of this model update. I'll go over some of these more important results that we have. So if we compare the runtime, it's actually the overhead compared to systems that are not providing the anonymity guarantee could actually end up being faster. And compared to the Bonavits, the other protocol that I showed, it's slower, but with respect to the number of clients, the growth of NFL, the runtime is actually slower. So the NFL runtime grows logarithmically, versus Bonavits is growing quadratically, right? So at most, for 512 clients, we're slower by 2x. I'll just finish up because we're out of time. I just wanted to give you like a final lesson based on all of this work that we did. And if there are any questions, I'll be happy to take them. So in real world systems, we sometimes need to have multiple requirements be satisfied at the same time, right? So in these examples that we saw, we needed robustness and privacy at the same time, right? And sometimes this would need to, for the systems to be designed from scratch, right? So providing this kind of multiple guarantees at the same time is not that trivial. And the research has to incorporate co-design a lot, right? So you would have to have understanding of the cryptographic protocols that you're using, the machine learning tasks that are used, and also potentially the hardware platform that you're running on, right? So we kind of, in my research group, address these aspects at the same time to be able to build systems that are getting closer to practicality for the guarantees that we need. Okay, I'll stop here and see if there are any questions.
Thank you very much, Professor. This was a great talk. Thank you very much. So now we can, I think, pass the floor to Atena for the technical questions.
Yeah, sure. Thank you so much. It was so informative. One of the questions that I have, and after that, I can let the audience ask their questions, is that when you talked about all these sort of security techniques that you use, can we use the same things for larger models like LLMs? Because when we're pre-training them, if we use all these security, will it take a lot of time? And especially because we have all these sort of gradients, using all these techniques on them, will it be too much for the server to handle it all, or it will work for them just the same way that it does for ResNet?
No, that's a very good question. So I kind of skipped over some of the results that we have, but in a lot of this type of protocols, let's say if you're using homomorphic encryption, you have to encrypt individual model updates, right? And that just grows, explodes with the size of the model, right? We would need additional optimizations to come in here. So for example, we have research that shows that when you're doing federated learning, a small portion of these model updates might be sufficient, right? So maybe in each round, I don't need to transmit all of the ciphertext corresponding to all of the model parameters, but only a particular portion. Right? Now, here there are some challenges arises because maybe how do you pick those, let's say, top K model parameters that are important for that round, right? And how do you ensure that no other private information is leaked here, right? So I think we need to further augment our solutions for this secure aggregation and so on with such optimizations to be able to scale it to very big models that are emerging.
I see. Thank you. Does any of the audience have any questions?
Actually, I have a question. So, so you said that like after the aggregation, the model, like the global model is published, like the model. Okay. The model owner has a
I
whole
guess we don't have Professor Ghodsi
professor.
anymore. Yeah.
Okay, I figured. Okay, let me pause.
Yeah, we can hear you good. Yeah.
Oh, yes.
Okay. You can go.
If you can repeat your question.
Yeah, sorry. So you said that like after the secure aggregation, the model owner gets the global model, like it decrypts the aggregation. So does that like because it's like in the middle of the training, does that reveal sensitive information because the model in the model owner gets the whole model between the
Yeah,
iterations?
that's a very good question, actually. So I didn't go over the details of the system, but to prevent those kind of issues, you also need to incorporate differential privacy, right? So this is exactly cryptographic techniques do not give you any guarantees about the output, anything that you can leak from the output, right? And that's why this differential privacy and cryptography sometimes work well together, because as it turns out in our case as well, because during computation you're hiding individual values by using encryption, for example, the amount of noise that you need to add is the only amount that you need for the output privacy, right? So this is kind of like the distinction between local differential privacy and global differential privacy, central differential privacy, right? So it turns out because the individual updates are protected by encryption, you can scale down the amount of noise, so the noise is only added for the revealing of the output model, right? And that's something we incorporate in the system as well.
Oh, great, great. Also, one other question is that like how do you compare if like for the work that you use zero knowledge proof, you use like ZK snarks. So how do you compare the performance of these two protocols?
Yeah, so again, this kind of depends on what are the efficiency requirements that you have. Again, generally, there's also a lot of work being done on the just development of these protocols themselves, and they have like different kind of guarantees, right? So a lot of times, actually, the work that has being done is to make sure that the verifiers are efficient, right? Because you want to make sure that this verification step can be done privately. But in this settings that we're working with federated learning, it might be the opposite, right? Because it's the clients with the limited resources that are doing that proof, right? So maybe we have to look for protocols that are the prover is more efficient, right? Yeah. So again, we tried experimented with I think the Wolverine that I mentioned and the ZK snarks and so on. They have pros and cons. But we were building this system such that they are not dependent on a particular protocol, right? You can, if tomorrow we come up with a better scheme, then we can plug it in, right? So I would say the main objective here is that to make sure that the prover is efficient, but again, we're not tied to any particular scheme.
Okay, great. Thank you very much. Thank you.
Excuse me, I had a question.
Mm-hmm.
So there was one part of your talk that you mentioned about clustering the clients first and then using the median of each cluster. I was just wondering what's the intuition behind doing that?
So the issue that I mentioned there is that, let's say we want to use a median-based aggregation scheme. Again, the point that I was making is that median is more robust to outliers versus just averaging is not, right? So a lot of this robust aggregation schemes are based on this median, or maybe a little bit more complicated versions of them, right? But that's the main idea. Now, if we were doing secure aggregation, you have to do this computation of the median also with cryptographic protocols, right? Which means that you have to be able to sort all of these updates that you have and find the median and so on, right? You have to do a lot of comparisons. Performing comparisons in cryptography is very expensive. So if you have a large array and you need to do all of these comparisons for this median computation, you're going to incur a large overhead, right? So that was kind of our solution to go around this issue. We, instead of computing the median of all the updates, we compute the median of cluster means, which can be revealed, right? And in that sense, we don't need to do this comparison in the cryptographic domain, right? But we show that still that kind of well-formedness check also works as well in protecting against attacks.
Okay, got it. Thank you.
Of course.
Thank you so much. I guess because we don't have that much of a time left, if there's no questions, let's give the floor to Yining.
Oh,